Hi, Dr. Compton. Thank you so much for coming. I have a bunch of questions, so if you don't mind, let's jump right into the interview. To get started, why don't you tell us your name and introduce us to your project? Sure. My name is Arthur Hawley Compton. I study the phenomenon that would later become known as Compton scattering, in which an X-ray incident on a solid target undergoes a shift in wavelength after scattering. Awesome. Tell us more about what you were trying to find with this project. While studying the arrangement of electrons and atoms through the deflection angles of X-rays, I noticed that the wavelengths of X-rays were longer after being deflected. This shift in wavelength does not agree with Thomson's classical scattering theory, so I began the experiments with X-rays on graphite targets as a means to explain this phenomenon. That's really interesting. And where do the experiments occur? It took place at Washington University in St. Louis, during my time as the head of the physics department there. So what other significant events were happening around the world at that time? World War I had just ended 4 years prior to the project's conception. During the time of the project, Benito Mussolini seized power of Italy, one of the many events that began laying the foundation for World War II. But on the topic of physics, Niels Bohr had just received a Nobel Prize for his investigation of the structure of atoms, which was a major leap forward in understanding atomic quantization. Well, since we're on the topic of other physicists, who else was involved in the project? I mainly worked alone on the project, but C.T.R. Wilson supported my theory with his invention of the cloud chamber. The cloud chamber allowed us to see the recoil of electrons after collisions with X-rays, further substantiating my claims. Wilson and I shared the 1927 Nobel Prize for Physics for our work surrounding this topic. So how would you describe your role in the project? Sure. I made the discovery of this phenomenon and also designed and facilitated the experiment in which X-rays were scattered by graphite. I then published my findings in Physical Review, which sparked a heated debate over the dual nature of light. I would like to follow up on those debates. How would you describe the impact your discoveries had on the physics community? My project confirmed the particle nature of light and the existence of photons through the principles of energy conservation and momentum conservation. If the wavelength of an X-ray increases after being scattered, its energy must be decreasing. But since we know that the energy must be conserved, we must find an explanation for this missing energy. If we use Planck and Einstein's interpretation of light being small packets of energy, this loss can be explained as an elastic collision between a quantum of light and an electron. This discovery was one of the founding principles of quantum physics and forever changed how we view light and energy. It sounds like Compton scattering had a huge impact on quantum physics. How would you say your discovery impacted your future work? This discovery deepened my curiosity about X-rays, and I continued to study them for many years. In my studies on X-rays, I discovered the phenomenon of total reflection and complete polarization of X-rays, leading to an accurate determination of the number of electrons in an atom. I was also the first to obtain X-ray spectra from ruled gratings, allowing for the direct measurement of X-ray wavelengths. Well, that's all the questions I have. Thank you for stopping by and teaching us more about Compton scattering. Thanks for having me.